Good morning, everyone. Today, we are going to start talking about titration. And hopefully everyone remembers the basic concept of titration from your chemistry class. So, let's write a couple things. So a titration is a technique used for chemical analysis which utilizes the reaction of two solutions. And we're going to have the analyte and the titrant. Okay, so the analyte is the thing that we're trying to figure out, and the titrant is the solution that we're using. This is the known. So this is our known. And this is what we're trying, this is what's being analyzed. So you have your analyte and your titrant. Now, in a lot of cases, and it's not always, but it's used to determine the amount of acid or base in a solution. This data will actually form titration curves. Sometimes they're called pH curves. And when we're making a titration curve, we're going to plot pH versus volume of titrant used. Now, there are four major points in a titration curve. Start of the titration. At the very beginning, all we have is analyte. So we haven't added any of our known yet. We haven't reacted any titrant yet. So this is at the very beginning. Then there's a region where the titrant is added. Up to what's called the equivalence point. And in this area, there's all that we have is unreacted analyte and product. Okay, so we start to add the titrant, and the titrant reacts with the analyte, and it produces our products. Right, so in this B region, all we have is analyte and product, and the amount of analyte is decreasing, the amount of product is increasing. C is the equivalence point, the third one. And this is the exact point where all the analyte has been converted to product. So the only thing we have at the equivalence point is product. That's it. All right, so our titrant has reacted completely with our analyte and produced all product, so we don't have extra of either. And then our D section is the region after the equivalence point. This is where we have excess titrant and product. So you have three regions on that graph. All right, and we're going to be looking at all three. Now, what do we use doing a titration? What equipment do we use? And hopefully you remember, right? So let's see. If you remember, we use burettes. We use 2 of them usually. We have 2 of them out. And then these have the graduations on them. Okay. There's a valve down here that we control. Okay, so hopefully you remember using burettes. Right? And these measure volume. Okay, and one would be the titrant, and one would be the analyte. So you'd start by measuring out a specific amount of analyte, and then we would slowly add titrant. Usually we use a Erlenmeyer flask, right? And we'll use a lot of the time we'll put a indicator in here. Okay, we'll put an indicator in there, right? And this is what we'll use. This is the piece of equipment that we use for our titration. I think I'm gonna try to do a lab with you with this. Titration is a really important technique in chem that you can handle. So it kind of makes me a little nervous that we can't actually do this, but that's why I want to do a lab with you. They can get pretty complicated, so I may just do a simple titration lab with you. Just so that you can see it being done and that kind of stuff. So we'll see how this goes. But we'll probably do some sort of lab with this. Probably next Monday, I'm guessing. All right. So here are our burettes. Now, what do these curves look like? And it really depends on whether you're using strong acids, strong bases, weak acids, strong base, strong acid, weak base. All right, and we're going to go through each one of those scenarios. So we're going to start by looking at curves when we have a strong acid, strong base, titration. Okay, so we're going to start with strong. So, for example, this is when we take HCl, which is strong, react it with NaOH, which is strong, and when this happens, we get water and Na plus and Cl minus aqueous. Okay, so this is an example of our strong. Now, what do the curves actually look like? Right, so let's be really careful with these. We're going to draw 2 graphs. So this is volume of titrant down here. And this is always pH and pH and volume of titrant. Now let's this one starts here and it goes like this, up a little bit, and then all of a sudden it juts up like this, and then it does this. And this, we're going to do the opposite. This is going to come like this, and then all of a sudden it drops like this, and then does something like this. Now, okay, so my pH is really low. All right, so let's say this is a pH of 0. We'll say this is pH of 14 up here. Okay, so you can tell that your analyte is an acid, right? Because my pH is starting low. So in this graph, my analyte, the thing that I'm trying to analyze, is an acid, which means our titrant is a base. Okay, so we add a base, we add a base, we add a base, and at first it slowly increases, then all of a sudden it shoots right up, right? And then it slowly increases. Over here, we're starting really high. So this is telling me that my analyte is a base. My titrant is an acid. Now, in a strong acid, strong base titration, right here in this line, okay, in a strong acid, strong base titration, this right here has a special name, okay? This is called the equivalence point. Okay, this is where all the acid, well, in this case, all the acid has been reacted with the base, and the only thing that we have is product. Okay, and for a strong acid, strong base titration, the pH of this is 7. Okay, because all we have is a salt and water here. Now, this is the same thing over here, right? So right here, this would also have a pH of 7, and this would be my equivalence point. Okay, this volume of titrant would be my equivalence point. All right, so let's look at what's happening here. Well, we're using HCl and NaOH. So we know that HCl, when we put it in water, will break into all H plus and Cl minus. NaOH is strong, and it'll do the same thing, and we'll go into Na pluses and OH minuses. So these completely ionize. So what happens when we put those two solutions together? Well, we have H plus Cl minus, and these are aqueuses, plus Na plus OH minus. Well, what happens? Well, the H plus reacts with the OH minus to produce H2O. What's left? Well, we have Na pluses still in that water and Cl minuses still in that water. Okay. Anyone remember what those are called? These are spectator ions. So really, what's the reaction that's happening here? Well, H plus OH minus is turning into H2O liquid. All right, so this is the reaction that's really happening. Okay, so this is our, it should be right here. This is the only reaction occurring. So if we look at this, okay, this is coming from the acid, this is coming from the base. So since this completely ionizes, for every 1 mole of this, we use 1 mole of OH minus, and we get a mole of water. All right, so we have this 1-to-1 ratio. All right, so every 1 mole of this, 1 mole of this to get this. All right, so strong acid, strong base titrations are actually pretty easy. Let's go ahead and look at a titration of one of these. Let's look at a titration of 50.0 milliliters of 0.200 molar HCl with 0.100 molar NaOH. I'm going to calculate pH during the course of the titration when specific volumes of NaOH have been added. So basically what we're going to do is we're going to kind of do 3 calculations at 3 different points on the curve. That's the plan. Okay. So let's start at the very beginning, of the titration. So let's calculate the pH of the analyte. Okay, and the analyte is the HCl at the start of the titration. So all we have to start with is our HCl, and we know that HCl is strong, and it breaks into H plus ions and Cl minus ions. Right, and the problem told us that we have 0.200 molar HCl. Well, since this completely ionizes, that means the concentration of H plus has to be 0.200 molar. Well, now I know the concentration of H plus. Concentration is 0.200 molar. So now I can calculate the pH. My pH equals the negative log the concentration of H plus. We do that math. Our pH is 0.699. Okay, so this is our starting pH. If we go back to our graph here, we're dealing with this one. So we're starting way down here. Right, now what we're going to do is we're going to start adding titrant, which is our NaOH. And this is what should happen. Right? It starts increasing slowly, and then all of a sudden it shoots up, and then it increases slowly. So what happens to this if we start adding some NaOH? Not sure that I really have enough room, so I'm going to go to a new page here. I'm going to keep this handy so we can go back to it. But all right, so let's do B. Let's add 15.0 milliliters of NaOH to the acid. Okay, we're going to add 15 milliliters of our titrant to our analyte. Now, remember, okay, we're using moles here. We're using the idea that 1 mole of this plus 1 mole of this will produce 1 mole of this. So we're comparing in moles, right? So we're going to have to be in moles. Now, in this titration, we have lots of acid, right? And we're slowly adding our base. So we have lots of this to start. And we want to know, hey, how much of this does it take to react with this acid? So we get lots of this. So in this, actually this equation, this turns out to be our limiting factor. Okay, so every time we add this, it reacts with this. Okay, now we're going to work in moles. We're going to work in moles. So that means we need to convert, we got to convert things to moles. So our acid molarity equals moles over liters. Our molarity of our acid was 0.200 molar. Okay, we want to know how many moles that is over 50 milliliters. 0.05 liters. So we have 0. What do we got? 0.10, no, 0.0100 moles. So this is how many moles of acid I have. How much base do I have? Well, molarity equals moles over liters. So we got, go back to our problem, we have 0.100 molar. X over, what do we just add? Oh, 15 milliliters. So 0.15. That turns out we have 0.0015 moles. Now, let's just, for fun, let's put this over here. So we know that we have 0.0100 moles of this. And we know that we have 0.0015 moles of this. We know that these completely react. So this is going to react with all of this. Okay, so this 0.0015 moles is going to react with this. So this is going to go down by 0.0015. This is going to go down by 0.0015. And we end up having none of this. And we have 0.0085 moles of this. Now I know this kind of looks like an ice table. It's not though, because we're really not dealing with concentration. But it is the same idea, okay? Remember, our ice tables, we're using molarity. Here, we're just comparing moles. So now, after we've added the OH minus, this is how much H plus is left in that solution. Okay, so this is the amount of H plus left after the base is added. Well, now we can do some things with this. We can convert this back to molarity. We know how many moles we have. 0.0085 moles. Now, be careful, because my liters have changed because I've combined the OH minus and the H plus. So originally, I only had 0.05 liters and 0.15 liters. All right, so I've put those together. So this is my total volume here. This is going to be my total volume. So I have to add the acid and base that I used. So this ends up being 0.0650 liters. So the new concentration of H plus is 0.13 molar. So this is my H plus concentration. Now, as soon as I have that, now I can go back and say, hey, okay, my pH equals a negative log of the concentration of H plus. My pH equals negative log of 0.13 molar. And my pH is equal to 0.89. Now, what did that do? Okay, what did that do to my acid from where I started? So we started, if we go back here, we started at a pH of 0.699. We added a little bit of base, okay, which raised our pH, but not a lot, right? Not a lot. So what's following? It's following this curve. Okay. Third point that I want to look at. Let's calculate the pH when 100.0 milliliters of NaOH is added. Go back to our equation. H plus OH minus goes to H2O. Okay. Now, again, we want to work in moles because for every 1 mole of this, we need 1 mole of this. It'll produce 1 mole of this. We're going to use that ratio. So now, we already calculated the number of moles of acid. Right, so this time, okay, we already calculated what we started with. Here it is. Okay, so here's our calculation for the amount of acid that we started with. So we started with 0.0100 moles of acid. Now this time, we're adding 100 milliliters. 100 milliliters of the NaOH. So molarity equals moles over liters. And our molarity to start was point. What was our molarity to start? 0.100 molar equals moles over, and our liters this time are 0.1. Right, so number of moles equals 0.0100 moles. So we're going to use 0.0100 moles. Look here. The amount of moles of acid is equal to the amount of moles of the base added. This is going to completely react. And only H2O is left. Well, when the concentration of H plus is equal to the concentration of OH minus, we know that the pH is equal to 7.00. And this is our equivalence point. Okay, this is our equivalence point when these are equal. Now, so where on the curve are we? Okay, so that's where we're right here. This is our equivalence point. we started here. We started to add some base. All right, we did a calculation somewhere in here. Then we kept adding base, and eventually it shoots up, and we reach a pH of 7, which is our equivalence point. And what we're going to do now is we're going to do one up here. Calculate pH when 125.0 milliliters of 0.100 molar NaOH is added. Okay, so let's go ahead. Again, we want to work in moles. So we're going to start with that same amount of acid. So we knew we had 0.0100 moles. Right? How many moles do we have this time? Well, if I do that calculation, molarity equals moles over liters, we end up with 0.0125 moles. Okay, so now let's just look at what we have. We know that we know this is strong, so this is a 1-to-1 ratio. All right, so which one are we going to run out of first? Well, all of the OH minus is going to react with the analyte. Matter of fact, we're going to have extra OH minus. All right, so this is going to go down by 0.0100. This is going to go down by 0.0100. I'll have none of this, and I'll have extra OH minus. I'll have 0.0025 moles of OH minus left. Okay. Now, I can convert this into molarity so I can get its pH. The molarity of the OH minus is equals to the moles over the total volume. Okay, so total volume. Right, so we know our moles are 0.0025 moles. Right, and our total volume is the total volume of our acid and our base added together. So that's, if we do that, it's 0.1750 liters. So our molarity is equal to 0.014 molar. And this is the concentration of OH minus. Well, now that I know the concentration of OH minus, we can do a couple things. We could calculate the concentration of H+, we could calculate POH and then convert to pH. Right, so there's a lot of different ways that we can do it. So I'm going to just do it this way. Our POH is equal to negative log of the concentration of OH minus. So POH equals negative log of 0.014 molar. So POH is equal to 1.85. Now I know that 14.00 minus the POH is equal to pH. So 14.00 minus 1.85 equals 12.15. And that's the pH of this solution. Does that make sense? Well, if we go back to our curve, so we started low, all right? We added, eventually it shoots up to my equivalence point, and then once we're above that equivalence point, the pH starts to rise really quick again, all right? So now we're somewhere up in here, which makes sense. Right, now, the other curve is just the exact opposite. You do it the same exact way, except this time our analyte is a base, and we're adding a strong acid, so it's just the reverse of everything that we just did. Now, a couple tricks. If we're strong, before the equivalence point, okay, so if we're before the equivalence point, okay, so down in here, up in here. The concentration of H plus and pH can be calculated by dividing the moles of H plus remaining by the total volume of the solution, okay, which is our acid plus our base volume. Okay, so for before that equivalence point, we're just going to take the concentration, we can calculate that concentration by just looking at the moles of H plus left and dividing it by my total volume. And then I have that concentration, I can calculate pH. Once we're after the equivalence point, that point, the OH minus and POH can be calculated by dividing the moles of OH minus remaining by the total volume of the solution. Now, these two things are for my first curve. All right, so when I'm starting as an acid and going to a base. Okay, if I was using this curve, this would be the exact opposite. Okay, now this is really what we just did, is we went through each one of those and we found out, okay, how many moles of H plus we had to start, and we divided it by the solution. So we did all this in our calculations. Okay, so this whole thing was for a strong acid, strong base titration. And this gives us a neutral salt. It gives us a neutral salt, okay, which has no effect on pH. Next class, we're going to talk about weak acid, strong base, and strong acid, weak base titrations. But we know something about the salt that forms from these. If we have a weak acid, strong base, the salt that forms is what? It's basic, which is going to affect our pH calculations. If we have a strong acid, weak base, the salt that forms is going to be acidic. Right? So these are a little bit more complicated. All right? And this is where we're going to go next class. So next class, we'll spend the class dealing with these two types of titrations, and then we'll talk about diprotic and triprotic and dihydroxy and trihydroxy titrations. All right, so that's the plan for tomorrow, or not tomorrow. I'm giving you tomorrow off for Friday. So Friday we'll deal with these titrations, and then I think Monday I'm going to try to do a titration lab with you. So that's the plan. You need to make sure that you're working through this stuff. So we're getting closer and closer to a unit test. All right, unit test will probably be Thursday or Friday next week. Thursday or Friday. I haven't decided. We have to do some other stuff still, but all right, if I had to guess, it'll be Friday, but I'm not sure. All right, so make sure you're working right along. And we will continue this on Friday. Have a good afternoon.